This is lecture 11E for Calculus 2. In this lecture we'll discuss examples of the power series. Recall from the first lecture that the power series had three scenarios for convergence. It could converge at one point, some value of x, well, x naught. It could converge in some interval about x naught. We denote that by using this radius of convergence r, or it could converge everywhere. So I'm going to give here examples of all three cases. So let me erase that screen for a minute. Okay. So this is going to be an example of a power series that converges only at one point. And here's the power series right here. I'll my pin again. Okay. So remember the power series has this form, n equals 0 to infinity of some coefficient n times, and this we're going to write it in general, x minus x naught raised to the nth power. And so that's what we see here. In this case, those coefficients are n factorial. So I'm going to expand the power series right here. You can see what it looks like. Okay, when n equals 0, x minus x naught to the 0th power is 1, so we just have 0 factorial, which is 1. The next term, I'll have 1 factorial, which is 1, times x minus x naught to the first power, then plus 2 factorial, x minus x naught squared, etc. Right. So now let's look at the ratio test. And the ratio test, here is the term a n plus 1. It would be n plus 1 factorial times x minus x naught raised to the n plus 1. Then here is the a to the nth term is n times x minus x naught raised to the nth power. Right. So obviously I can do some arithmetic here. I can subtract the exponents on the x minus x naught terms. I can expand the n plus 1 into n plus 1 factorial into n plus 1 plus n factorial and cancel the n factorials. And here is the result of the ratio test. N plus 1 times the absolute value of x minus x naught. Right. The limit as n goes to infinity is infinity for all values of x except x equal x naught. For x equal x naught, the limit is 0. This power series converges only, oh, that's supposed to be only. Let me get a pin here. This is only at the point x equal x naught. In the second example, the power series will converge on that with that second scenario. It will have a ratio, a radius, about x equal x naught, in which the power series converges. Here we're going to use the power series expansion for the arctangent of x. And here is the form right here. Alright, it looks a little more complicated than we usually have. We've got our c to the n. Let me find the pin. So here, c to the n equals minus 1 to the n over 2n minus 1 whenever x is odd, and when x is even, c to the n equals 0. And we end up with it in an expansion. Here's the expansion. 1 minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, etc. Now we're going to construct the ratio test by looking at neighboring values, neighboring terms in the series. So a to the n plus 1. Actually, when you start working this through, you find that the minus 1 to the n isn't an issue because you're taking the absolute value. Right. Now you're dividing by 2n minus 1, that's why it appears in the denominator here. Then you would be when you're dividing the denominator by 2n minus 1, and so that's why it ends up here in the numerator here. Otherwise, for the a n plus 1 term, what's remaining of its coefficient ends up in the denominator. Okay. By subtracting those exponents, doing a little bit of work, we get 2n minus 1 over 2n plus 1 times x squared. Right, that's our ratio. Now we're going to take the limit as n goes to infinity. When we're taking that limit, we can divide numerator and denominator by n and end up with 2 minus 1 to the nth. Of course, as n goes to infinity, this goes to 0, and also in the denominator, the 1 over n term also goes to 0. So we're left with x squared. So the limit of the ratio test is x squared. And there were 3 scenarios again for that ratio test. If that limit is greater than 0, the series diverges. If it's greater than 1, it diverges. If it equals 1, then it's inconclusive test, and if it's less than 1, then the series converges. So we have to look at these 3 cases. Okay, x squared, strictly greater than 1, it's going to diverge. X squared, less than 1, it's going to converge. X squared equals 1, it's inconclusive. So x squared is less than 1 if x is less than 1. So this scenario for convergence right here requires that x be less than 1. So repeating here, or summarizing here what we did on the other slide, this limit, the limit of the ratio test is less than 1 only for absolute value of x less than 1. This gives us the radius of convergence r equals to 1. So we know that the series expansion for the arctangent of x converges between, in the open interval, minus 1 to 1. We still have questions concerning the endpoints. That is when x is equal to minus 1 or when x is equal to plus 1. To check for the convergence at x equals plus 1 and x equals minus 1, let's substitute those values into this power series expansion for the hyperbolic, or for the arctangent. So for x equal 1, we substitute and we get this alternating series, 1 minus a third plus a fifth minus a seventh, etc. When x equals minus 1, we get the same results, although starting with a minus 1, and then the signs alternating. Both of these are good candidates for the alternating series test. The conditions of the alternating series test are listed here. The series will converge by the alternating series test if all the terms are positive. That means all the a to the n's are positive. The signs, of course, are changing. Right? And that's the case here. We do have 1 minus a third plus a fifth. They're all positive. The terms are decreasing. That means a to the n minus 1 is always either less than or equal to a to the n. In this case, of course, it will go, we're looking at 1 over n plus 1, n plus 2 is less than 1 over n. Okay, so they are decreasing terms. And if the terms themselves converge to 0, and they do converge to 0. So by the alternating series test, this series converges at the endpoints x equal plus 1 and x equal minus 1. And here's our conclusion for this particular power series. This power series expansion for the arctangent of x converges for absolute value of x less than or equal to 1. Now we have an example of a series that converges everywhere. So for this, we're going to use a very famous series expansion of e to the x. And the expansion for e to the x is x to the n divided by n factorial. And here's what the terms look like: 1 plus x squared over 2 factorial plus x cubed over 3 factorial. I really like this series. It's very symmetric and quite beautiful, actually. And it converges to e to the x everywhere. So to show this, we're going to use this ratio test. Ratio test, we take a to the n plus 1 divided by a to the n, because we're taking the absolute value here, because we need those positive values. And by doing a little bit of algebra, we end up with absolute value of x divided by n plus 1. Now we can take the limit as n goes to infinity. As n goes to infinity, of course, this goes to 0. I'm going to review again the 3 criteria for the ratio test so that you can be learning that along with the series. You can be reviewing it, rather, along with this power series discussion. If the ratio test converges to some value that is less than 1, then the series converges. If the ratio test converges to the value 1, the test is inconclusive. If the ratio test converges to some value L that's greater than 1, the series itself diverges. In this case, the ratio test, the limit of the ratio test is 0, therefore this series converges. And this holds for all values of x. I'm going to talk about a slightly different topic, or quite a different topic at the end of this, right now at the end of this other lecture, but I didn't want to break it out as a separate lecture, so it's right here. And this is concerned with operations on the power series. Since this is calculus, there are two operations we're very concerned with, and that is differentiation and integration. Now for these power series, you can differentiate them term by term. So let's look first, just give you an example here. Here is an expansion for the natural log of 1 plus x. Right. And its radius of convergence is 1, which we didn't prove here, but I'm going to mention it. And this is actually a half-open interval. So let's look at that expansion, and it's x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, etc. So if I apply the derivative operator to both sides of this equation, I'm taking the derivative of the natural log of 1 plus x. The derivative of that, analytically, is 1 over 1 plus x. On the right-hand side, I'm taking the derivative of this series, which means I'm taking the derivative of every single one of these terms. Now I can only apply the derivative operator on the interior of the interval of convergence. The interior of this interval of convergence is the absolute value of x strictly less than 1. But I'm going to apply it there, okay? And when I do, I just start taking the derivative of each term, using the typical linearity property of the differential operator, and I get this sequence. This series. 1 minus x plus x squared minus x cubed, and it continues. The next term will be x to the 4th, be minus x to the 4th. This is a result I'm getting analytically, and the question is this valid? So what we're going to show now is that this, whoops, how come that's so? Is that this series does indeed converge to 1 over 1 plus x. So let's look at this series right here. This is what we got by the termwise differentiation of the expansion. We got 1 minus x plus x squared minus x cubed plus x to the 4th. This is a geometric series. It's n equals 0 to infinity of minus x raised to the nth power. Now what do we know about this? A geometric series, this one will converge for the absolute value of minus x strictly less than 1. Well, that agrees with the radius of convergence that we were working with previously. And what does it converge to? It converges to 1 over 1 minus the term in this parentheses is raised to the power. Okay, so it's 1 minus negative x, which is 1 over 1 plus x, which is what we got on the right-hand side, or the left-hand side of the equation previously. So analytically, what we've done on one side is taken the result analytically and got 1 over 1 plus x. On the other side, we differentiated the series term by term. We got an expansion that indeed converged to the analytic answer we had on the other side. Of course, if you have the analytic answer, there's probably very little reason for doing the term by term differentiation, although sometimes you might use that to numerically plot or calculate values for transcendental functions. Now let's look at integration. We can also integrate the power series, and we can do that by integrating term by term. Okay. So let's say we have the integration for sine of x, which Taylor series, we haven't derived that, but you might know it from the past. It's fairly well known. So the sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and going on. Now I want the sine of x squared. So I can use this expansion, and x being a variable, I can substitute x squared for x. Right. When I do that, I end up with the sine of x squared is x squared, that's instead of just plain old x, minus, of course, x to the 6th over 3 factorial plus x to the 10th over 5 factorial. Now let's integrate. The integral of sine x squared dx does not have an elementary transcendental function representation. It doesn't have a closed form solution in terms of the elementary transcendental functions. So I'm just going to leave it like that. I'll leave it as the integral of sine x squared. And now I'm differentiating this series expansion. Here's just the first 3 terms. Right? I'll end up with, of course, just using the power rule, x to the 3rd over 3 minus x to the 7th over 7, but it has to be multiplied by this 3 factorial from the original expansion, and then next to the 11th over 11 times, and then I have the 5 factorial from the expansion of sine x squared. The integral of sine x squared, or in this case we're using tau under the integral sign, is a Fresnel integral, s of x. There's the Fresnel integral for sine, and there's another one for cosine of x squared. These occur in gratings and diffraction in optics. You'll encounter these, but they have a life of their own too. So this is a Fresnel integral, is the integral from 0 to x of sine tau squared d tau. So it's the same as this. What is the expansion for it? It is exactly this expansion. Of course, that's where they got it, since there's no analytic, there's no closed form solution for the integral of sine x squared. And it's written like this. You'll see it's written like this in textbooks or handbooks. It's the sum from n equals 0 to infinity of minus 1 to the n, so you're going to have your alternating plus minus. It's going to start plus, right, because minus 1 to the 0 is 1. So you have that alternating sign you see right there. It's included in this term. Now, x is raised to the 4n plus 3. When n is 0, it's cubed, okay, first term. When n is 1, it's 7. When n is 2, that'd be 2 times 4 would be 8 plus 3. There's your 11 right there. Okay, there's our power of x. In the denominator, we have 2n plus 1 factorial. That will give us these odd terms here, the 3 factorial, the 5 factorial, etc. And then this is multiplied by 4n plus 3, which is the same as the power, and that's what we're seeing here. Again, this is called a Fresnel integral. It is not an elementary transcendental function, but it is a transcendental function. It is a result of the integral of sine x squared dx. And we have achieved this result by integrating term by term the series expansion for sine x squared.